Hello, everybody, and welcome to the virtual seminar series on Bayesian decision-making and uncertainty. My name's Alex Turenin. I'm with Cornell and one of the organizers who's going to be hosting the event. I'd like to thank my fellow organizers, Si Wang, Natalie Mouse, and Renato Berlingeri for their work in helping to put the series together. So before we get started today, I'd like to just make a few announcements. First off, we still have one more speaker who's going to present this seminar, during this season of the seminar that will take place next week. And you can find the schedule for that presentation on our website, which is gp-seminar-series.github.io. And yeah, check that out. You can join seminars via Zoom as long as you register for the Google group to get an email with a Zoom link, and the instructions for that are on the website. Or you can always watch us on YouTube, which doesn't require any registration. Seminars take place at 1600 UTC. And if you're joining us on Zoom, excuse me again, you can ask questions by typing them in the chat, and the speaker can choose to take a pause and answer the questions, or if they prefer, they can hold the questions at the end. It depends on the speaker. And with that said, for today's seminar, it is my great pleasure to introduce Marvin Pförtner, who will tell us about computation-aware Kalman filtering and smoothing. Marvin, take it away.
All right, thanks, Alex. Let me just get the screen share started. I hope you can all see that now. Yeah, all right. Yeah, thanks for the introduction. I'm Marvin. I'm a PhD student in Philipp Hennig's lab at the University of Tübingen. And I'm basically going to present a recent AI stat submission that I presented like a couple of weeks ago in Thailand. So with that, I'm just going to dive right into the problem statement. Because, well, I suppose in this crowd, I don't really need to say this, but I'll do it anyways. GPs are just cool. They're really powerful and flexible Bayesian models for basically any sort of function learning task. But we also probably all know that they're fairly expensive if we implement them naively. So we obviously know about the cubic time complexity in the number of data points for computing the posterior GP. But arguably, what's probably even worse is the quadratic memory scaling that we get in these methods. And as sort of a running example throughout this talk, I'm going to be talking about spatiotemporal regression a lot because that's one of the areas that I'm mostly interested in these days. And here, the number of data points is sort of a product of the number of time points that we consider and the number of data points that we consider in space at each of these time points. So effectively, we get like a sort of sixth power and fourth power here, which is obviously unacceptable in just many scenarios. And we need to fix this problem. Luckily, there has been some previous work on this that reduces the class of GPs to specifically considering Gauss-Markov processes and in one input dimension. So if we just consider time as the input dimension, there's a lot of work on using Gauss-Markov processes that admit linear time posteriors by essentially replacing the typical matrix inversion by Kalman filtering and RTS smoothing algorithms, where here now our prior is actually typically represented as solutions of linear SDEs. And we observe them through some linear observation model at a finite set of time points. And then this same construction pretty much can also be repeated for the spatiotemporal setting, where we consider these evolution type stochastic partial differential equations that, well, essentially have the same structure. We have an infinite dimensional state space here now, and observe through a linear operator that is then perturbed by some Gaussian noise, but that maps into a finite dimensional space again. But I mean, we never actually implement these infinite dimensional state spaces on a computer, obviously. So how is that typically done? And that's also something that is fairly common in the literature already. I'll just use a fairly simple example here to illustrate what's going on, and particularly popular class that's being used throughout the literature a lot is this class of space-time separable Gauss-Markov processes, where both the mean, that's actually a typo, that's supposed to be mu here, and the covariance function are products of covariance functions in time and covariance functions in space. And then the nice thing about this is if we have such a space-time separable Gaussian process and sort of a set of data points that's essentially the union of training and test data points, we can instantiate the infinite dimensional state space by pre-discretizing and then assuming that this covariance function in time admits a Markov representation. So if the Gaussian process that we form by sort of just considering the time component of this process is Markov, then the entire thing discretized at these pre-selected data points is also a Gauss Markov process. And we can write down the transition densities of this. This is a fairly large object right here. So the number of spatial data points comes into play here. But what's important to note is that within the transition density of this Gauss-Markov process, we have Kronecker products. And essentially, because of the structure of these Kronecker products, we can very efficiently multiply with these matrices without actually instantiating these big matrices in memory. And that's going to be very important later on. Now, once we've discretized such a process at the temporal locations at which we observe data points, what we obtain is a linear Gaussian state space model. And just to fix notation, I'll just reiterate here. So essentially, the idea is that we start with some Gaussian initial state, U0, at sort of time point 0. And then the dynamics of the unobserved latent process evolves as an affine transformation of the previous state, basically. And then we add independent Gaussian transition noise at every time instant here. And we observe said process through another linear transformation H with Gaussian observation noise epsilon also independent being added at every state, or at every time point rather here. A fairly useful property of this is that we can actually immediately compute as a recursion the moments of this prior at time point k, essentially by just recursing the mean through the affine part of the transition model and then recursing sort of always the previous covariance function through just the linear part and adding the noise covariance of the dynamics process onto it. And that's a representation that we're also going to make use of later on. Inference in these models is very classically being done by the Kalman filter, where the Kalman filter algorithm computes the so-called, what we sometimes refer to as the filtering posterior. So the marginal belief about state UK, given all data points before and including the current time point that is being computed recursively. So specifically, the moments of that process are being computed recursively, essentially by, at every state k, conditioning these pk minus matrices, or rather the state that has this pk minus matrix and this mk minus vector as its second and first moments, respectively, just by linear Gaussian conditioning. It's a fairly standard formula, I suppose. And then the state that has these pk minus and mk minus states as its moments is sometimes referred to as the predict state. That is essentially part of the forecasting posterior, which is just the states UK conditioned on all the previous data. And then the filter interleaves these two steps to compute the final filtering posterior. If we go into the complexity analysis of this, and let's just focus on the case of spatiotemporal regression for now, then we can already see that from the sort of sixth power that we had before-ish, so the cubic time in the number of temporal data points and the cubic time in the number of spatial data points, we now reduce this to linear time algorithm in the number of temporal states, but still cubic in the number of spatial data points. And the memory requirements also drop to linear now, but from quadratic in the number of time, but still a number of temporal data points. And depending on how this actually is implemented, this basically, if states don't need to be kept around, if we don't actually need access to the entire posterior, this can also be just quadratic in space as well, just to put that out there. But this is only a partial solution to the problem, obviously, because in a lot of spatiotemporal regression scenarios, the number of spatial time points is still quite large. And so we can't really afford a quadratic memory cost in those data points and a cubic time complexity in these data points. So there's two main challenges arising from this, which is that in the algorithm, even just to represent these state covariances pk minus and pk, which are d by d matrices, where d is the state space dimension in spatiotemporal regression, that is effectively the same or a multiple of the number of training points, like spatial training points. So these need to be stored in memory, and that requires d-square space, which is absolutely prohibitive for large data sets. Like the example that I'll bring later on is basically sort of a climate modeling example where the state space is essentially points on the surface of the Earth, and as the resolution of that becomes sort of realistic, so as we move to smaller and resolving smaller and smaller scales in space, yeah, absolutely prohibitive to even just store one of these matrices, let alone over the entire time series. And then the second challenge is basically one that we inherit from Gaussian conditioning, which is that the pseudo inversion of the innovation matrix or the Gramian in the Gaussian conditioning step of the filter, that is number of data points or number of observations by number of observations, that has a cubic time complexity to compute. And also, again, this probably arguably worse quadratic memory complexity to just even represent the matrix in the first place. So we need to address these two challenges for these algorithms to be actually useful in like very, very high dimensional settings. And that's what, yeah, our project that I'm presenting here does. And to sort of illustrate how we tackle these two problems, I'll start with the second challenge. And then we'll see that the first challenge actually sort of, a solution to the first challenge arises from that. So let's start with challenge 2. The innovation matrix is, well, hard to represent or intractable to represent densely in memory, but also quite costly to invert. And here, let's start with an observation, which is that very often this Gramian has a very rapid spectral decay because it amounts to a kernel matrix for these separable spatiotemporal models, for example, but also other classes of models. So this is especially in spatiotemporal regression. And then because we have rapid spectral decay, it's often a good approximation to just project on a low-dimensional subspace this that represents the top k eigenvectors of this matrix that already gives us quite a good approximation of the inversion. So yeah, that's basically what we do here. And we can achieve this in a quite nice way, computationally speaking, but also from the UQ standpoint, by just projecting the observation model, which remember is just yk equal hk uk plus epsilon k. And we project that onto a matrix of actions, this S matrix. So the columns of this matrix are called the actions, where this is basically thin, so sorry, tall. So we have a lot less actions than we actually have data points. And basically because of that, the resulting projected Gramian is also only going to be nk check by nk check, which we deem feasible to represent in memory and then actually embed. The nice thing about like projecting the Gramian by modifying the observation model is that now our algorithm is actually informed about this projection. And in computing the posterior, it's going to be conservative in the uncertainty quantification, basically because that down date that we get in Gaussian conditioning is going to reflect the fact that we projected on a lower dimensional space. So that makes the algorithm, well, that's one of the components that makes the algorithm what we call computation-aware, is that we make an approximation to the computations that we can't quite afford by this projection, but we inform the inference mechanism about this, so it can basically account for the error inferred by this approximation through the linear Gaussian inference mechanism here. And you might be asking, well, how do we actually like choose these vectors S? Because obviously we can't just compute an eigendecomposition here. That would be just as prohibitive. We might as well just solve the linear system in the first place. But we can use tools from different areas of numerical linear algebra. In this work, what we found worked the best was using the Lanczos process to compute approximations to the eigenbasis or the top k eigen vectors here in a matrix-free way, that is without actually instantiating the matrix G in memory, and basically at quadratic cost in the number of original observations. And we get quite good approximation quality and fairly strong theoretical guarantees for the convergence of this procedure. But there's other choices of actions that might be more suitable for other kinds of particular problems. We could use random actions from like basically randomized sketching methods, sketch and project method, sketch and solve methods, sorry. Yeah, and so this I've already said, modifying the observation model makes the entire algorithm computation aware. All right. So this solves challenge 2 to an extent because we still need to be able to represent GK. And that's related to the challenge 1 because, well, to even compute the GK matrix, we need some way of representing the state covariances. So both the predictive covariance and the filtering covariance that are d by d dimensional. And this absolutely needs to happen without incurring O of d square space. So a realization that we've had is that we can actually represent these matrices as down dates to the prior at time point k. So remember that in the original Kalman recursion, we always refer pk minus and pk back to the respective matrices at the previous time instant. But here we actually reach back into the prior instead of that. And then we can write them as these, what we call down dates, these like left square roots mk minus and mk of the term that is being subtracted in Gaussian conditioning. There is a bit of a problem with that because if you go through the algebra of this representation, we actually build up rank of these down dates. It's the sum over, if we actually at the same time apply the projection that I've presented on the previous slide of the projected ranks here, and that is obviously a bit of a problem. I'll address this a little bit later on. Just stay with me for now. And now the important thing is that instead of recursing on the state covariances pk minus and pk, we can actually recurse on the down dates. So instead of predicting forward on pk minus, we predict forward through the linear part of our transition model on the down date of the previous updated state. And to compute the update step for the filtering posterior, we just append columns to the predicted down date from before. And that's actually what causes this build up of rank here over time. So this recursion leads to a matrix-free implementation of the Kalman filter, essentially because we can very often represent the prior covariance matrix, sigma k here, without instantiating the matrix in memory. And that is like particularly easy to see in the kernel case where we actually start from one of these separable covariance functions. Yeah, where we just basically need to store the spatial locations and the functional form of the kernel, like the spatial part of the kernel, and then can multiply with it by essentially not memoizing the entries. So computing the entries of the covariance matrix on the fly while doing the multiplication. That brings the memory cost down to linear in the number of data points as opposed to quadratic in the number of data points. All right, and then basically putting these two ideas together, we get the algorithm that we call the computation-aware Kalman filter. If you squint at this, obviously this is a bit of a wall of text situation going on right here. You can kind of recover the traditional structure of a Kalman filter. So we have a predict step, which predicts forward on the previous updated mean with our affine part of our transition model. And then it also predicts forward basically on the covariance function, sorry, on the state covariance. But now, because we need to represent everything in terms of the down dates, it happens on the down date. And then the update step is also pretty much the same as in a traditional Kalman filter. It's just that we first modify our observation model by projecting the relative quantities. And then when updating the covariance, we also only update the down date here instead of the full state covariance. And that we do by appending these columns here. So I just called this a matrix-free method, and we got this feedback actually a lot when reviewers ask us questions about the paper. There's matrices all over the place. Like how exactly, why do I call this matrix-free? And I've already outlined this, is that we don't actually retain any sort of intractably sized matrices in memory. That's kind of what we mean by matrix-free here. And it's specifically that, well, we can represent the prior's covariance in this efficient way that I've outlined, where basically this is a kernel function and we just need the data to retain the data points, and then the matrix multiplication just instantiates the entries of the kernel matrix on the fly, just storing the data points. All right, so I've already hinted at the fact that if we implement things in this way, we get a bit of a build-up of rank in these down date terms. And basically, that is problematic because now we get a build-up over time. So assuming that we choose on the order of O of 1 projected observations at every time step, which is a reasonable assumption, or that is also often made in numerical linear algebra for these kinds of methods, this very quickly scales quadratically in time again. And that's obviously unacceptable if we're in a streaming data scenario where we maybe don't really know how long we want to predict for. Or just have a lot of temporal time points. Think like a large scale climate simulation, maybe or weather simulation that should run sort of for quite a long time to produce sensible results here. There's luckily a fairly simple solution to that though, which is just we can truncate these down dates after updating them at the update step. And that's just basically being done by writing them as this outer product. So we take the square root factor of the down date and write it as a sum of a smaller down date, mk plus. So that's going to be what we take as our down date after truncation. And then there's some remainder term here, nk, that we're basically going to throw away when predicting to the next state. And basically, there's a lot of degrees of freedom in this decomposition here, but a particularly nice one is one that we obtain by computing the SVD of this down date, because then we can show that this rank truncation is actually optimal in terms of any unitarily invariant matrix norm. So that basically we drop as little certainty information as possible. It might be a bit difficult because of this, because we're doing another approximation that we're not necessarily accounting for. But it turns out that if we truncate in this way, because we truncate the down date, that is essentially representing directions in which we're more certain about the state that we're trying to infer here. This can be interpreted as a computational noise model that after truncation adds what we call computational noise to the state. That is basically noise incurred not by an actual measurement process, but rather because we just simply can't afford computationally to represent the state in this way. And so we make the uncertainty quantification actually more conservative after truncation, which is like, I suppose in terms of UQ, kind of the correct direction. You never want to be overconfident, but underconfidence is in most scenarios probably okay. And also the truncation error we incur here, especially in stationary processes, is actually quite low, because this transition matrix A that we used in predicting the next state is actually an exponential of this matrix F with eigenvalues that are lower than 1. So yeah, we have an exponential decay in the spectrum here as well. And then essentially this amounts to augmenting the graphical model of the original prior by these new states UK plus, which amount to taking the updated state and then truncating its down date afterwards by adding this computational noise. And that's going to be fairly important when we later talk about the smoother, because the smoother needs to account for the removal of this noise here to be sort of probabilistic probabilistically consistent. Maybe an interesting connection here is that we can equivalently derive the CAKF as an embedded probabilistic linear solver that actually solves that intractable system defined by the Gramian against the residual that appears in the conditional mean, so in the update step of the Kalman filter. And then what essentially happens is we get a random variable belief over the representer weight, so over the solution of this system that we then propagate just by linear closure of Gaussians under linear operation to the conditional mean. And that way we can actually also derive an iterative version of what I presented as like this batch form, where we get all of the actions at the same time and project the Gramian onto a batch of actions. What we rather want to do here is select these actions one at a time so we can like early stop this procedure should we detect that, a rank of or projection rank of a given number is enough to represent the problem. So you want to do some adaptive choice of projection dimensions here. And actually also the nice thing here is that through our sort of exterior model, through the dynamics of our Gauss-Markov process prior, we push the belief of this probabilistic linear solver forward to the next state where we then employ another probabilistic linear solver. So basically we use what is effectively the posterior belief of one probabilistic numerical method as the prior of another. So we basically have a computational chain here where multiple probabilistic numerical methods are used to inform each other about basically the solution of a related problem, which is kind of one of the long-standing dreams of the field. All right, so this is mostly what I wanted to say about the filter for now. I'll go on to talk about smoothing here, and just to go back to the basics for a second. So if we want to compute the full Bayesian posterior, so the marginal state belief at time point k, when we condition on all of the data, not just on basically the present and the past, that's typically computed by the so-called Ratung-Streibel smoother, and it's a backwards recursion that reuses the iterates of the filter and sort of walks backwards through time from the last observed data point. The problem here is that there is another matrix inverse in here, and that's actually a d by d matrix inverse, which is typically much larger than the number of observations, like spatial observations. So that's, in a sense, even more intractable than the inverses we've seen before. But luckily, we can make a bit of an observation here in the recursion. When we start this recursion at the end, so basically at nt here, we can see that this term right here simplifies if we plug in all of the values into just a quantity that doesn't involve any additional inverses. And basically massaging this algebra through all the way to the beginning, we can see that there is a sort of an algebraic simplification of the RTS smoother that doesn't involve any additional inverses that we haven't computed during the filtering step. I realize there's a bit of let me actually open a window real quick, sorry. I realize there's a bit of a wall of text situation going on here. This is mostly in here to inform you if you ever need to implement just your standard RTS smoother, you don't actually need inverses. We haven't really found this in the literature, so I'm not sure whether this is new, but it's really useful for sure because we found this to be much more numerically stable than the regular RTS smoother. So maybe as a bit of additional, like as an additional goodie, if you don't want to use our smoother, you can at least use this thing that's algebraically equivalent to the regular RTS smoother. And basically, if we stare at this for long enough, we can see that there's already this type of like down date going on in this recursion that we chose for the filter as well. So we just use the same representation for the smoother as well. By this theorem, we can see that we can refer the smoother states back to the filter states and recall from before that the filter states themselves can be written as prior down dated by basically a small matrix. And then there's just another down date going on here. So that put together basically means that we can represent the smoother covariance as the prior covariance matrix downdated by one of these downdate, well, these like outer product type downdate terms here, where now an additional concatenation in the columns to the downdate square root that we've already got from the filter before. And then the nice thing here is that if you recall from the filter derivation, this also decomposes into the addition of columns that come from the update step at that particular point. So we get this sort of these sorts of three partitions within that matrix that correspond to the belief that came to the current state from the right, so from the future, the belief sort of the directions of certainty that we obtained by conditioning on data that we've observed at this time point, and directions of certainty that we attain by the data that came sort of from the past. So this is very, very, I think, illustrative in sort of the information flow in the algorithm. Yeah, and then we can just implement this. It's also a bit of a wall of text, but importantly, it's also a backwards recursion, just like the regular RTS smoother. The equations are a bit unwieldy, but we actually found them to be quite numerically stable, and that's mostly because of the fact that we don't need additional inverses here. And then because we again concatenate new columns into this downdate square root here, we need to keep the rank of these downdates low as well, and we basically do that by the same truncation procedure that we already ran during the filtering pass, just backwards in time now. All right, let's talk a bit about some experiments that we did with this. All of the experiments that I'm going to show you here are spatiotemporal regression problems. We've, I think, for all of them used a Matern 3/2 process in time for the temporal part of the covariance function, and mostly a Matern 5/2 kernel in space. And then for the first few examples, for example, for this one, we've just sampled data from this prior and perturbed it with the appropriate amount of noise that is encoded in the observation model. And that's mostly because of the fact that we wanted to isolate the performance of the algorithm and not necessarily incur errors that we get by model mismatch to like any real world data. So this is really just to isolate the approximation made, or how bad the approximation is made by the algorithm. So obviously, this being published at a machine learning venue, we need to compare to some baselines here, and the sort of workhorse for high dimensional state estimation, arguably the sort of de facto standard, are ensemble Kalman filters. So we've chosen two instances of these methods here. Basically, the idea behind ensemble Kalman filters is that you do a low rank approximation of the state covariances, as opposed to doing a low rank approximation of the downdate to set state covariances that we do here. And you can see that our approach of truncating the directions of certainty versus truncating the entire sort of uncertainty structure that we learn in the covariance matrix is actually quite beneficial, especially for low computational budgets. So basically these plots, the data, so the scatter points here in these plots amount to an increasing computational budget that's given to each algorithm. So for the ensemble methods, that's the rank of the approximation. And for us, it's the rank of the downdate that amounts to the number of iterations that we do at every step in this like Lanczos procedure. And you can clearly see that the algorithm here starts to perform really well even after, and this is, I think, rank 1 in the downdate. So basically, we just see one projection, a one-dimensional projection of the data at every time point. This already performs quite well in terms of like fit of the posterior mean. But what's really remarkable is that this is like 10 orders of magnitude better, even at the beginning, in terms of the metric that assesses the uncertainty quantification, which is the average negative log density of the posterior when we plug in the ground truth states. And that's essentially because we actually have mostly a full rank covariance function, or covariance state covariance at every state, because we only downdate by rank 1, whereas these methods represent the entire uncertainty in a rank 1 subspace. So it's actually quite natural that you would expect this uncertainty quantification to be really rather bad, especially because this is on model. If we compare to their the standard counterparts of the computation-aware Kalman filter and smoother, then we can see that the error stays nice and bounded over time. And so this is the ranks that we chose in the approximation. You can see what you would expect, that the error goes down the more down-date directions you allow for, and also the more sort of mean iterations that you allow for when fitting the posterior mean. We also isolated the effect of the truncation in an experiment. So you can basically see here, we run for a different number of iterations at every step when we update, but we don't truncate at all. And then here is basically the same plot, but we run truncation where we we truncate the rank of these down dates to twice the number of iterations that we do at every given step when we update. And that's basically because we want to retain some of the information that we sort of get from the past when forecasting, and give the algorithm just some space to rearrange the directions in this way. So we don't only get the sort of I new directions at the state, but can also retain I old directions that we've obtained at previous states. And then we obviously wanted to see how far we can kind of push it. So what we did was we took a fairly large scale data set from the climate sciences. That's called ERA5. It's a global reanalysis data set where I think just about like 100 years of climate are being, or climate observations rather, are being assimilated with a dynamical model into this like super nice and dense time series that contains, for example, the Earth's surface temperature at a fairly fine scale grid. So the grid of the version of the data set that we've been using is kind of like I think this is like a roughly 1440p image that is then unrolled onto the globe. The temporal resolution of this data set is an hour. And for our experiments, just to have a bit of a handle on the dimensionality of the data set, we actually downsample this by factors of 3, 6, 12, and 24. And then we use a regular subgrid of this for testing and the rest of the data points for training. And as a model here, we again use this Matern 3/2 prior in time, but also use an extrinsic, so a manifold kernel, an extrinsic spherical Matern 3/2 covariance function for the spatial part. So basically to get a Gaussian process over the sphere here. Just to give you some stats about this experiment. So basically I'm talking about the largest instantiation here, where we only downsample by a factor of 3. This gives us 90,000 training points per time step. The state space dimension then is, I believe, around like 250,000. And we have 4.2 million training points in total. So that's already quite a respectable size for GP regression, I think. We did like, I think, 48 hours of like temporal range, I suppose. So we selected a 48-hour window from this data set. The result here is from the one of the smaller scales, I think from the 12 scale. So this is from downsampling the data set by a factor of 12. You can see that this makes the Earth's surface temperature somewhat blurry. There's, I think, a message in the chat. Yeah, it's 48 time steps. It's hourly resolution. Yeah, and then we take 48 hours. But I mean, we could have chosen this for longer, but we really like the main sort of problematic factor here is really the spatial dimension, because the algorithm scales, the regular Kalman filter scales cubically in time and quadratically in memory in that. So yeah, we could have basically run this for longer. It's a bit limited in that sense, but it actually scales to the sort of state space dimensionality. So this is technically still a regime in which we could apply a regular Kalman filter, but now if we go to the version of the dataset that we only downsample by a factor of 3, we get a 250,000 dimensional state. I calculated this, and I believe just to represent a single state covariance would take on the order of like 1.5 terabytes of RAM, let alone doing any computation on that. And our algorithm here to represent the covariance of this this state that we see here takes like megabytes. I think it's like roughly 500 megabytes or something like this. So that's already quite a big improvement, but we buy this by actually this rather gnarly looking uncertainty here, which is, I have to say, maybe the main drawback of this method right now. There's sort of two components going into this. So first of all, why is the algorithm this underconfident? We can see that the mean actually is fit like fairly well, I would say. But this isn't really reflected in the uncertainty. And that's basically because if you think about it, because we project our down dates onto this low dimensional subspace, we don't really remove all of the uncertainty from the state. So we just fall back to the prior in regions where we haven't really seen any data. And this, combined with some convergence properties of these probabilistic linear solvers, leads to these underconfident beliefs. I have some theory about this later on as well, which, sorry, there's something. Let me say training, which parts need training? So we don't. Yeah, that's a good point, actually. So the question is, when you say training, which part needs training, the GP hyperparameters or what? When I say training here, I mean like conditioning on data points. We didn't use hyperparameter optimization here yet. This is a bit in the works, but this is also a way to fix the underconfidence of the uncertainty here. Basically, we just fall back to the prior outside of the regions where in the regions where we haven't seen any data. And so the obvious solution to this is just to get a better prior for the problem here. The length scale of the spatial part of this Matern process was basically set to, I believe it was twice the distance of grid points at the equator. So obviously that's like kind of the worst case scenario for GP regression in general, where it's a very short length scale. There's no sort of global information encoded in the covariance structure. And that's an easy fix. We just kind of ran out of time implementing this. And I think fixing like prior year would actually quite massively improve the situation in terms of uncertainty quantification. And we also get this nice plot here over time, where you can see that there's quite some non-trivial structure going on in the mean. The uncertainty doesn't really reflect that. But again, I think this is mostly fixed by hyperparameter optimization, plus maybe using slightly different choices of actions. I should maybe also say, and Alex is probably going to be happy to hear this, that we don't just have efficient representations of the moments of the states, but we can also sample from the posterior, provided that we can draw samples from the prior. And that's basically because we derived a version of pathwise conditioning that uses the structure of the Kalman filter. So it only Kalman filter and smoother, I should say. So it only reuses quantities that have already been computed to transform samples from the prior into samples from the posterior of the GP by just basically leveraging the algebra that Matheron's rule dictates that we should use here. So let's move on to some short details about our theoretical analysis of this algorithm, because that also gives us some insight into what's going on with the uncertainty quantification. So first of all, computational complexity, I'll make this fairly quick. There's some assumptions going into this, which is basically that we can efficiently multiply with all of the matrices involved without actually synthesizing the matrices in memory. That mostly means it shouldn't cost more, like efficient here means it shouldn't cost more to multiply with these matrices than it would cost to multiply with the dense versions, like if we actually instantiated them. And then we also basically set the number of state space dimensions equal or on the order of number of data points observed in space that is uniform across time. And then if we do that, we can see that the worst case complexities of the CAKF and CAKS are actually, as we wanted to, we drop basically one order on the sort of spatial complexities, if you will. So we still retain the linear complexities in time, but we now have a quadratic scaling with the state space dimension in time and a linear scaling in memory. Here, again, the same thing applies. If we don't run the smoother, we can bring this down to NT and check. So we don't actually have linear scaling in time anymore. And yeah, if we compare this to the regular version of the algorithm, we essentially drop one of the powers on the D's here. So that's good. That's essentially something we can handle. I want to talk very briefly about a error bound that we've derived from very classical results in scattered data approximation, specifically for the spatiotemporal regression case. The idea here is that our prior is one of these space-time separable Gauss-Markov processes from before, and then we observe the zeroth component of that. Basically, that is because we do a state space construction. So we actually augment the state with temporal derivatives to be able to represent higher order Markov processes, typically. And yeah, we then assume to have a fixed set of spatial training inputs. We call Z train here, and we take some arbitrary given test input Z that we sort of augment the state with. And then we can show that our the posterior covariance, so basically if we take the state covariance evaluated at an arbitrary test input, and then the zeroth component of that, add the observation noise of the observation model, take the square root of that, that's a pointwise tight worst case error bound on the relative error when we compare the true data generating function yz, which we assume to be an element of the RKHS of this predictive GP here, to the mean estimate that we give here. And basically, there's an important thing to point out here, and that's a fairly typical form for these like GP error bounds actually. We have on the right-hand side something that is essentially an expectation over our state, whereas on the left-hand side, we have a supremum, so a worst-case estimate. So essentially, we see that a tight error bound that is actually that can actually be attained for some given data generating function y here, yeah, is equal to the worst-case error bound here, and that's maybe a bit of an insight into why the uncertainty quantification is as conservative as it is. But again, basically by estimating the hyperparameters, we can bring this closer together. Yeah, and with that, I conclude for now. Thanks to my amazing collaborators on this project, Jonathan Wenger, John Cocaine, Philip Hennig. Happy to take any questions.
Thanks so much, Marvin, for the talk. So the way that we're gonna, just to make a little bit of organizational announcements, the way that we're gonna handle questions is there will be an initial period of questions. We've had a couple of them during the talk, but we're gonna have an initial period of questions that will be broadcast on YouTube so that our YouTube listeners can follow along. And then after that, we will conclude the live stream and we can have a sort of more open-ended discussion that isn't being recorded or broadcast for anyone who prefers to not be recorded. So if you have, if any of our viewers on Zoom have any questions, please feel free to put them in the chat and then Marvin can address those. Thank you.
So there's a question in the chat. What do you think will remain the big limitations of this work as this work and follow on is developed? That is a good question. I think the main issue here and the sort of main driving cost is the multiplication with the covariance matrix. So that maybe there's two components to this. So basically using dense covariance matrices here, and so given this need to actually recompute the entries of the covariance matrix in this matrix-free style, that drives the computational costs quite high. So it's actually, in a sense, it's more costly, not asymptotically, but like in walk clock time to multiply with these lazily represented kernel matrices. So if the kernel that you use as a prior isn't really adapted to the actions that you use. So for example, sparse maybe, doesn't lead to a sparse kernel matrix, and that costs quite a bit. So for just to give you an example, for this like Earth surface temperature example, even to just generate 48 hours, a 48-hour interval with 48 time steps, the filter actually ran, or the filter and smoother together actually ran something like 5 days on a GPU. I have to say, like, we could have made some more specific choices here that could have driven this cost down quite substantially. Like, for example, using sparse actions, which obviously massively increase the computational efficiency of multiplying with the kernel matrix. Using sparse kernels is another one where the matrix vector product becomes quite a bit less expensive. But yeah, so right now, if you don't make use of any structure, it's fairly expensive to multiply with this, even on GPUs. The other thing is that as compared to traditional Kalman filters, we actually have this requirement that we need efficient access to the marginal state the covariance of the prior, so the sigma k term, at every state. And that's something you don't actually have for all state space models. It's just not necessarily available in closed form. So that limits the applicability of the algorithm as it stands right now. Definitely. And we mostly focused on this spatiotemporal regression case, where very often you actually do have that covariance function available in a form that you can multiply efficiently with. But yeah, it doesn't just apply to any state space model. You need that structure where you have an analytic expression of the marginal state covariances.
Okay. And so unless there are any other last-minute questions, I think we will now move to conclude the live stream. And before we do so, I wanted to thank all of our listeners on YouTube for joining us today and remind everybody that there will be one more seminar for the season, which is coming up next week. And you can find information about that on our website, which is gp-seminar-series.github.io. And please feel free to check that out, sign up, and potentially join us next week. Thank you so much.